So now we're going to move on to bases. I'd like you to turn to worksheet 17 in your packet for our notes. We're going to look at some bases. So for the Arrhenius concept, which we learned earlier, a base is a substance that produces OH ions in aqueous solution, or hydroxide ions. The Bronsted-Lowry definition is that a base is a proton acceptor. We need to know both of these definitions because some of our bases are not as simple as our alkali metals, so like sodium hydroxide or lithium hydroxide or potassium hydroxide. So our simple bases like sodium hydroxide and potassium hydroxide fulfill both criteria, and they dissociate completely. Strong bases dissociate completely, just like strong acids dissociate completely. All hydroxides of group 1, the alkali elements, are strong bases. All group 2 hydroxides are also strong bases, are alkaline earth metals. And 2 moles of hydroxide are produced for each mole of compound. But they're not very soluble, so they're really good for antacids. So aluminum hydroxide, magnesium hydroxide, they don't dissolve in the mouth or your throat or your stomach, but they dissolve with excess stomach acid to cure indigestion. If you think about it, they neutralize H+. So you have extra stomach acid, which is H+. You're going to add something like OH-, and you're going to turn that extra stomach acid into water, which is why they work. So the pH of a strong base is sort of similar to our pH of a strong acid. It's going to be pretty straightforward. We're going to calculate the pH of a solution made by putting 4.63 grams of lithium hydroxide into water and diluting it to a total volume of 400 milliliters. List the major species. Well, it's water and LiOH, and that's the only thing we need to list. The reactions that produce hydroxide ions, LiOH, becomes Li plus OH-. Choose which reaction will dominate the OH production. Well, it's going to be that LiOH reaction is going to dominate it. If it is a strong base, which it is, the OH will be equal to the molarity of the base. Just like if it's a strong acid, the H+ will be equal to the molarity of the acid. So we need to calculate the molarity. So we have 4.63 grams of LiOH. We're going to convert that to moles. It's 23.94 grams, and it's equal to 0.193 moles of LiOH. And for finding the molarity, that's moles over liters, which is 0.4 liters. And so we end up with 0.484 molar. And then if we scroll down a little more, the concentration of H+ can be calculated from Kw. So Kw is equal to 1 times 10 to the minus 14. Remember, that's a constant, which is equal to H+ times OH-, and H+ is equal to, oh, and I can put in, instead of this OH-, I can go ahead and put in my 0.484. And so if I take 1 times 10 to the negative 14 and divide by 0.484, I'm going to end up with 2.07 times 10 to the minus 14. And then it says to calculate the pH using the hydrogen ion concentration. So now that I have it, pH is equal to the negative log of 2.07 times 10 to the minus 14, and I end up with a pH being equal to 13.68, which makes sense. It's a basic pH for a basic problem. If I had gotten an acidic pH, something I need to look back and check on. So let's go on to worksheet 18 for notes. And it says many types of proton acceptors, bases, do not contain the hydroxide ion. So this is our other type of base. But when they're dissolved in water, they increase the concentration of the hydroxide ion because of their reaction with water. Our most common and most used example is ammonia and derivatives of ammonia. So ammonia acts as a base because it's a proton acceptor. If we look at how ammonia is drawn, back to geometry, it's here and it's sitting here with that extra pair of electrons. This is where an H+ that has no electrons would just come in and park itself to make that NH4+. So it says to label the acid, the base, the conjugate acid, and the conjugate base. So we know that ammonia is our base, which means water must be acting as our acid. And we know that our conjugate acid is going to be what gained the proton, and our conjugate base is going to be that hydroxide. Bases such as ammonia often have an unshared pair of electrons that is capable of forming a bond with a proton, just like I showed you up here. Most of these bases have N with a lone pair. So all of these here act in the same exact way. They have a nitrogen that has a lone pair of electrons sitting out there waiting for a hydrogen. The general reaction between a base and water is given by B for the base plus H2O yields BH plus OH minus. So if this is our base, then this is acting as our acid, this is our conjugate acid, and this is our conjugate base. So to write the Kb expression, we're going to take our products, BH plus and OH minus, and put it over the concentration of our reactants. We are not, do not ever include water. The concentration of water does not change, and so we would not include water. If I were to write the Kb for the expression up above with ammonia, I would write NH4 plus OH minus over NH3. So the Kb always refers to the reaction of a base with water to form the conjugate acid and the hydroxide ion. It's exactly the same step. The leaving out of water is not anything new or different. It's a liquid, and so we have to remember not to include it.